I'm John Lee. I'm a 2005-2006 SPE Distinguished Lecturer. I'd like to thank the SPE Foundation for their financial support for this lecture program. My lecture topic today is Advances in Unconventional Resources Technology, specifically assessment methodology. I'd like to motivate this discussion by looking at the situation that we find ourselves in throughout the world in energy availability. And I'll note that global energy availability really requires some creative thinking. Despite what we may read or hear in some of the media, we really don't have a worldwide shortage of hydrocarbon energy today. We simply can't readily transport all the forms of hydrocarbon energy from where they are produced to where they're needed. We need more hydrocarbons near markets. There are several solutions to this problem, but among these, widely distributed unconventional resources really should help this situation. And improved assessment methodology is one of the keys to availability of these needed unconventional resources. Now, to further understand the particular role that unconventional resources can play, let's focus our attention on the United States. And I want to look with you in this next slide at some history and then some projections through the end of the next generation for unconventional U.S. gas production. The information that I'm presenting here was developed by the Energy Information Administration and published in its 2006 Energy Outlook. What I've shown here is a plot of the annual energy production in trillions of cubic feet versus time. The historical period is from 1990 through the end of the year 2004, which was the latest information the EIA had when it made this forecast. And first we see the history and then the projection of lower 48 conventional onshore gas. And what we see in this graph is a downward trend through history and a continued projection of downward trend in production of lower 48 conventional gas onshore. Offshore gets a lot of publicity, but again, the history and the projection suggest a downward trend. Lower 48 associated gas associated with the production of oil. Flat at best. Now, a bright spot is Alaska. Been very little production from Alaska of importance. That's projected to change somewhere in the range of 2011 to 2015. And of course, the key will be the potential development of a pipeline from Alaska to bring gas to the lower 48 states. Even so, once that pipeline is completed, the projection is for flat production of gas from Alaska and really not a highly significant fraction of total production. Now, the one bright spot in the sources that I'm showing you here is through history. For the last 15 years, you see a significant increase in production of unconventional gas in the lower 48 states, and that's projected to continue to increase through the year 2030, through the end of this human generation. I'd like to read a quote from you, which comes from the EIA Energy Outlook in 2005. It's a rather dramatic quote, and I think we can use it to help make an important point. The EIA in that annual report noted that as a result of technological improvements and rising natural gas prices, natural gas production from relatively abundant unconventional sources and these include tight sands, shale, and coal bed methane. That's projected to increase from 35% of lower 48 production in 2003 to 44% in 2025. That was the end of the projection in the previous energy outlook. From 35 to 44% of total U.S. production. So, cutting through all the detail, the bottom line is that as a percent of total production, we see gas from unconventional sources growing from 35% to 44% over this roughly 25-year period. Unconventional resources are expected to be extremely important in our immediate future. Why is this going to happen? Well, one driving force is technological improvements are going to allow this to happen. Another is rising natural gas prices, and maybe saying the same thing but in different words, a diminished supply of conventional resources, which in turn is largely responsible for these rising natural gas prices. These are the drivers. Now, what I've shown you was for the lower 48 states in North America. I also have reached the conclusion that this same sort of increase in importance of unconventional resources will occur throughout the world, except in most places later than in the U.S. So I've shown the same sort of graph here of production of unconventional resources as a function of time, increasing over time for the same reasons that I have indicated in the U.S. In areas where there's a shortage of natural gas now, areas such as parts of Latin America, areas such as India, areas such as China, the need is now. And the driving forces are there to develop the unconventional resources. In other areas, this increase in production of unconventional resources may be many years in the future. Areas like much of the Middle East, areas like Russia, where there are tremendous reserves of conventional hydrocarbon resources. Even in those two cases, I've been interested to find in my discussions with some people in the countries that there is at least some development of unconventional resources even now. For example, in Russia, there are a lot of large oil fields which have begun to deplete and to continue to produce at high volumes. The Russians have begun to develop some lower permeability reservoirs, either above or below the conventional reservoirs, lower permeability, and they've used hydraulic fracture stimulation to begin to develop some of those resources. So it's happening now for special reasons. I've been surprised to learn that in Saudi Arabia there has been some development of tight or lower permeability gas formations for purposes of providing fuel for field operations, for a matter of convenience. But these are just the opening wedge. The big driving force will be later when the need for energy cannot be supplied with conventional energy in these various parts of the world. Now, to further understand the unconventional resources, I think it's helpful to look at what I'll call the resources pyramid, which is illustrated in this next graph. In this pyramid, which is illustrated on the graph, I show the highest quality reservoir at the top of the pyramid and the lower quality reservoir at the base, or as we approach the base of the pyramid. The size of the resource we find in many studies of occurrence of natural resources in nature shows us that we have relatively lower amounts of the highest quality resource, that near the top of the pyramid, and much larger amounts of the lower quality resource near the base of the pyramid. There is at any time in our field operations a limit below which development of the resources simply is not going to happen because it's not commercial. We might oversimplify and call that a practical permeability limit. There is a reservoir permeability below which we simply can't afford to develop the resource. And having mentioned can't afford, I think we might really generalize and say what we really have with these resources is a practical cost limit. For a certain lower quality of resource, lower permeability, lower productivity, or perhaps higher cost because of a remote location, for resources of that higher cost, we cannot afford to develop them. But the important point is that as technology advances, as prices increase due to diminished supply, this barrier will tend to move down the pyramid and open up these vastly greater amounts of resources for consumption in the world's markets. The National Petroleum Council in the United States, that's a group of representatives from industry that does studies to advise the U.S. government from time to time as need arises. This group did a study of gas resources in North America and published the study in 2003. And so I refer on this slide to an NPC study in 2003, the notes you see in the lower right-hand corner of the slide. All right, in this study published in 2003 and mostly completed, say, in 2002 or a year or so prior to publication of the study, this group of representatives from industry, practical people, not ivory tower people, but people taking what they believe to be a realistic look at what's likely to happen, again, through about a human generation. They looked at a brief period of history and then made projections into the future as to what the total gas supply through North America would like to be, and presented those results as trillions of cubic feet of annual production versus time over this study period. All right, the curve that I have shown on the slide now shows the results that come from no advancement in technology, with technology frozen in place as it existed at the time of the study. And again, this same group, a realistic group, without making unreasonable claims, saw that with foreseeable advances in technology, that the increase in natural gas supply, certainly by the end of this study period in 2025, would really be substantially greater than what would be possible with the technology that existed at the time of the study back in 2002. Year by year, there's not expected to be a huge amount of increase in production, but the cumulative effect overall was expected by this group to be very substantial, as you can see on this graph. All right, what are these expected technology advances, which is going to increase the supply? Well, I've broken these advances into two different areas. I'll call these a group of technology advances above the line, and then we'll look at a group of technology advances below the line. Those above the line include improved exploration well success, improved development well success, improvements in ultimate per well recovery, improvements in initial production rate, and the average annual increases over the 25-year period of the forecast are modest at best, but the cumulative increase over the 25 years, you see, varies from about 11% to about 24% from among these various technologies. That is clearly important. The technologies below the line are probably what most of us think about first. These are reductions in costs of operations as opposed to simply improved ways of doing things, although these reductions in costs clearly do represent improvements in these technologies too. For example, drilling costs are expected on average to continue to decrease over this forecast period. Reductions in cost of completions. And for unconventional gas resources, this is largely stimulation costs, the costs of hydraulic fracturing and related technologies. Reductions in construction costs, reductions in fixed operating costs. And together, again, they're expected to be significant advances and contributions to increased supply from improvements in this technology. Well, in the remainder of my discussion, I'm going to focus on the technologies above the line because these technologies have to do with enhanced resource assessment in finding and quantifying the volumes of unconventional resources, particularly in North America and then later throughout the world, these enhancements in technology that we can expect to increase the supply. At Texas A&M University, we formed a research group, sort of a coordinating group called the Crisman Institute. And in this group, we have representatives from operators in industry who look at proposals that we make or listings of technologies in which we think we have sufficient experience to be able to conduct research and improve technologies. We circulate these lists, and industry people in response say, okay, among these things you guys say you can do, here are the particular topics that we are most interested in and that we are interested in funding. And in our Unconventional Resources group in particular, in this Crisman Institute, we have found that two of the more popular and more completely funded activities include, first, quantifying the uncertainty in unconventional gas resource assessments in North America. And second, then estimating the unconventional gas resources outside of North America, particularly in countries where there is a near-term need to begin to develop these resources. And some of our sponsors are international operators, but some of them have focused their activities mostly in North America in the past and are looking now to begin to expand in their unconventional resource development throughout the world. Okay, so we have industry sponsors who say we're interested in developing more technology in these two areas, and let's look at the first one in improving our ability to characterize unconventional resources in North America and quantifying the uncertainty. How shall we proceed with such a project? Well, it's always wise in a project like this to look what others have done and try to build on that. And in looking at the various methods that have been used in the industry in recent years, we pretty quickly found that the U.S. Geological Survey had developed a methodology in the mid-1990s and had begun to apply that methodology in a series of studies of important sedimentary basins in North America. And the first published result of these applications was presented in 2003. Here is a look at some of the important sedimentary basins in the U.S. that contain important amounts of unconventional resources. Well, the USGS, in this first published study, this first widespread application of their technology for resource assessment, did a detailed study of the Uinta-Piceance basins in western Colorado and in nearby Utah, as illustrated in the red on this slide. All right, what attracted us particularly to this USGS methodology? Well, as we'll see later, it's more quantitative assessment of uncertainty than any previous methods. How did they go about this? How did this quantitative assessment, which appears to be superior at least to other methods published in the public domain, exactly how did they go about this? Well, the USGS approach was first to identify areas within a petroleum province, a sedimentary basin or a subset of that sedimentary basin, that are so-called total petroleum systems. That is, they're hydrocarbon source rocks, they're reservoir rocks, they're hydrocarbon traps. All this is quite conventional thinking. And then the USGS broke these areas into so-called assessment areas. Now, in the industry, we have referred to assessment areas, or what the USGS calls assessment areas. That's roughly equivalent to what we've called plays. There are about 700 of these in North America. What the USGS has done is to break these assessment areas into cells. And so here we show a typical assessment area broken into cells. The areas of these individual cells is roughly the expected drainage area of a well drilled within that particular unit. All right, the next step in the USGS methodology, which we found to be interesting, was the fact that the USGS classified a petroleum system either as conventional, and on this slide I've identified 3 different kinds of conventional petroleum system. On the left, there's a conventional structural gas accumulation with gas in a structural trap above water. In the middle of the slide, there's a conventional stratigraphic gas accumulation. And then on the far right, there's a conventional structural oil accumulation. The other classification that the USGS used is that of a continuous accumulation. Now, there are 2 examples on this slide. First, I want to note the scale here. It's obviously qualitative, but we're talking about tens of miles here. And we show a continuous gas accumulation in the lower part of the slide covering many tens of miles. This gas accumulation, notice, is in the bottom of a sedimentary basin, and it sort of disappears. It has diffuse boundaries, but there may be a transition zone between accumulation and then non-accumulation. The important point is that the gas can be found everywhere throughout this accumulation, continuously, with no gaps. Also, we show typical coal seams near the surface in the top part of the slide, very large, and again, continuous over very large areas. Now, again, what the USGS has said is an accumulation is either conventional or it's continuous, and therefore continuous is essentially the same in this approach as unconventional. Let's look at some characteristics of conventional and then unconventional accumulations to help distinguish between the two. A conventional accumulation is characterized by having a relatively higher matrix permeability. It has obvious seals and traps, as I illustrated on the previous slide. It tends to have relatively higher recovery factors. By contrast, the continuous accumulation tends to be regional in extent. It has diffuse, ill-defined boundaries. It tends to have relatively lower matrix permeabilities. No obvious seals or traps. No hydrocarbon water contacts. It tends to be abnormally close to source rocks. In fact, the source rock in these accumulations is often contained within the sedimentary basin, which ultimately is productive. These sorts of accumulations tend to have relatively lower recovery factors. These continuous accumulations in the USGS mode of thinking include tight sandstones, coal bed gas, oil and gas in fractured shales, and chalks. Now, I want to note before I continue describing the USGS methodology that there are many people, good thinking people within the industry, that simply don't accept the USGS model for unconventional resources. And in one published paper, Shanley and others, Shanley is a prominent geoscientist in the Rocky Mountain area, and he and others published a study of the Green River Basin, not too distant from the Uinta-Piceance basins in the Rocky Mountains, and they found evidence that there were a lot of lower permeability, what we would usually call unconventional gas resources, a lot of lower permeability gas fields that occur in poor quality rocks, but in quite conventional traps. That is, limited in extent, perhaps trapped structurally, and except for reservoir quality, very much like conventional accumulations. Now, this is a critically important issue as to whether all unconventional resources are continuous accumulations, or whether this may happen some of the time, but in other cases where we may have these lower quality resources occurring quite conventionally. The topic was so important that the American Association of Petroleum Geologists convened a special forum to deal with this subject a couple of years ago. And representatives from both sides presented their points of view. Shanley and others presented their point of view. The USGS presented its points of view. Neutral observers at this conference concluded that there was no consensus. They concluded, many at least did, that probably there's truth in both camps, that some unconventional resources do occur as continuous accumulations. Some probably don't. It's very important, though, to recognize that these continuous accumulations, if that's really the correct model for virtually all unconventional resources, what that means is that anywhere we drill a well, there will be hydrocarbons that will be producible. Not necessarily commercially producible, but producible. And as costs go down, or as prices of gas go up, as technology advances, we'll be able to recover more and more of this gas that is found to be everywhere. That would be true if we accept the continuous accumulation model. But if many of the important unconventional resources occur in conventional traps, that gas, a lot of that gas is simply not there. And you can drill all the wells you want to, but you won't find any gas. And so it shouldn't be included as part of a forecasted resource base. So that's an important disagreement within the industry. What's the appropriate model? All right, back to the USGS methodology. The USGS, within these cells in the accumulation units that I pointed out earlier, for those areas that have already been drilled, they simply use production decline curves for gas, for example, or for oil, and simply projected these decline curves into the future down to some, let's call it economic limit, to determine the estimated ultimate recovery from that cell. And they did it for all the wells within the unit, and in that way came up with a distribution of estimated ultimate recoveries for the entire accumulation for that part of it that has already been developed. And so here we have a distribution, estimated ultimate recovery in millions of cubic feet of gas or thousands of barrels of oil versus percent of sample having that particular EUR. All right. This particular distribution, then, modified as needed, is used to make some forecast about what's likely to happen in the part of the accumulation unit that has not yet been drilled. And so it's possible to come up with a complete probabilistic distribution of what to expect in the future. All right, the USGS study team then applied this approach to the Uinta-Piceance basins, as I've said earlier, and came up with some results for hydrocarbons that have not yet been discovered, but which are part of our potential resource for the future. And I've divided this into oil and gas and conventional and unconventional. All right, for conventional oil, the study team concluded that the mean value is about 20 million barrels of undiscovered oil in these basins. That's not a large amount. That's not a big target of a great deal of interest to large operators. More importantly for our purposes is the fact that the USGS came up with a complete distribution of these hydrocarbons with 95% probability. That's the P95 number on the slide. They estimated that the industry would be able to produce about 7 million barrels. And with 5% probability, they estimated the industry might be able to produce as much as 40 million barrels. Again, with a mean value of about 20 million. For continuous oil, again, the mean value is just under 40 million barrels, not a large number, with a spread from 32 million barrels expected to be recovered with 95% probability up to 56 or 57 with 5% probability of occurrence. There's a complete probability distribution here, and we're just reading off some of the key numbers. For gas, conventional gas, again, not much by industry standards, 213 billion cubic feet mean value with a spread again. The big undiscovered resource, not surprisingly, is the undiscovered continuous or unconventional gas with a mean value of about 21 trillion cubic feet. 95% probability of 12 trillion, 5% probability of as much as 34 trillion. I want to emphasize again, though, that these numbers are based on the assumption of continuous accumulations, that wherever you drill within an accumulation unit, that there will be producible gas, not necessarily commercial today, but much of it convert commercial eventually. Focus on this continuous gas number. Notice the spread between the 95% probability number and the 5% probability number. A spread from 12 to about 34 trillion cubic feet. For something as poorly described, as unknown as this is, that's not a very large spread between what's going to occur with high probability and what might occur if everything goes well. There's a great deal of uncertainty there. This study has appeared to many observers in the industry to not really completely capture all the uncertainty that's really present in what's likely to be discovered. All right, I want to mention that and some other important points from this study in this next slide before we go on. This USGS methodology does yield a probability distribution of undiscovered resource. And it's unique among approaches that are in the public domain of yielding that probability distribution. Most previously published work simply presented a most likely case and a pretty subjective and ill-defined high side case and low side case. We're trying to do better than that. We're trying to come up with a complete distribution. The USGS is clearly on the track that I think is going to be important for the industry in doing that. Second observation that I'd like to make about this study in Uinta-Piceance is that virtually all the undiscovered resource in that model was continuous gas. And therefore, the validity of the continuous accumulation model is quite critical. And the third point is one that I emphasized when we were looking at the table of results, and that is that the range from P5 to P95 is surprisingly narrow. Well, this is where our study team thinks it may have been able to make some contributions. We had access to all the data that the USGS used, and we've had a lot of cooperation from USGS. Our look at their analysis indicates that the input data into the study, things like what's the area of the accumulation unit itself, pretty narrow typically for the various accumulation units. There were 16 of these, as I recall, in the Uinta-Piceance Basin. Not much variation between the low value and the high value for each of those units. Not sure that we really can be that certain about something that's that ill-defined. USGS made a lot of use of triangular distributions. And in looking at the ranges of those triangular distributions, such as what is the area of those accumulation units? What's the lowest number? What's the most likely number? What's the highest number? Those ranges, again, they appeared to be quite narrow. And finally, and importantly, it's a technical detail that we can't get into too much here, but to help the study teams, which began doing this kind of work back in the mid-1990s, rather than use full Monte Carlo simulation of these various distributions, the study team used some analytical approximations so that it could do its work more readily at remote study locations from point to point. And in looking at that method of aggregation and then comparing it with Monte Carlo simulation, which we can readily do today on laptop computers that we can take anywhere, we find that the accumulation method itself can have a significant impact on the distribution of resources. I'm not going to go into details, but I will note that we've made some suggestions to enhancing what we think is already the best approach that has been used by the industry, and our suggestions are published in a paper which is being presented at the Low Permeability Gas Symposium in the Rocky Mountain area in 2007. All right, I'd like to go from that problem, which is, as you'll recall, quantifying the uncertainty in unconventional gas resources in North America. I'd like to go from that to the second project that we said we had, and that is estimating non-North American unconventional gas resources. And set the stage here. Let's consider the typical international basin. Let's say the Sichuan Basin in China, to name one example. That basin has some conventional resources, and if it follows the law that all natural resources do, we know that these are relatively limited in amount. And then it has unconventional resources, which are almost certainly much larger in extent. And then let's take a typical North American basin. It has conventional and unconventional resources, and we have this cost barrier dividing between conventional and unconventional in both cases. Now, in the North American basins, very mature basins, where we have been studying for a long time how to develop increased resources for current needs. We know a lot about the distribution of the conventional resources within the important sedimentary basins, and we know a lot about the unconventional resources. These have been well studied in North America. By contrast, in our typical international basin, there's a lot known about the conventional resources because this has been what market forces have driven operating companies to develop, but there's virtually nothing known about the distribution of the unconventional resources in these international basins. So therein lies the problem. How are we going to solve this problem? We've taken the approach of developing basin analogs. And let me elaborate on that. Here we show a number of North American basins with their known amounts of conventional and unconventional resources. Here's our frontier basin, a basin in China, a basin in Argentina as examples, where we know a lot about conventional, very little about unconventional, simply because in the past there has been virtually no incentive to study the unconventional resources. And we're going to use an analog basin approach to try to help us quantify the potential for the resources in these frontier basins. We've developed some software. We'll use the acronym BAS for Basin Analog System, and we've developed the first version of this software with a lot of help from people from industry and from our sponsors. What the basin analogy software does, it predicts unconventional hydrocarbon resource potential. It's intended to be a guide for exploration to help us determine what areas look like they might be potentially important. In the software, we are estimating the reservoir characteristics for that unknown, unconventional part of the resource pyramid. We're tying what's known about these kinds of potential resources to what have proved to be the best engineering practices in the well-studied basins in North America. Best drilling practices for that type of resource, best completion practices, best stimulation practices. How have we gone about developing this basin analogy software? Well, briefly, starting with a literature review, then determining parameters to use in our analog, important characteristics of these basins. We've looked at 60 to 70 North American basins as a starting point, identified those with significant unconventional gas potential. There are maybe 30 to 31 of those. And for these important basins, we have developed summaries of the geological and petroleum system characterizations. Those parameters that, on the basis of expert opinion, appear to be important in determining analogies between different basins. And using this approach, we've developed the basin analog system. And the way that we do this, we take a given target basin and we compare it and what's known about it to the 30 or so North American basins about which we have considerable information. We compare the frontier basin to each of these North American basins. We determine which is most likely to be a good analogous basin. Of course, to apply an approach like this, we have to validate our results by making some predictions where we sort of know the answer, and that is working with some North American basins, treating them as unknown in their unconventional resources and predicting closest analogies, and then see how good a job we do of predicting what is known to be the correct outcome. We've gone through this as far as we can. There are probably years and years of work ahead of us to refine a system like this, but the basic idea seems to be working. All right, I'd like to conclude now with some summary comments on the most important points that I've tried to make in this discussion. First comment that I opened with that's of significance is that unconventional resources, particularly gas, are clearly going to play a leading role in the North American energy supply in the next 25 years. I've also made the point that unconventional resources are also going to play an increasingly important role in the world energy supply, not necessarily in the next 25 years, but certainly in coming decades, in some places sooner than in others. I made the point that advances in technology are clearly a key to developing the potential of these unconventional resources in North America and worldwide. I noted that our ability to assess resources better and to quantify uncertainty more accurately, that's an important part of technology development. I believe that the USGS methodology for resource assessment is a good, in fact, it's an excellent starting point. I will note that widespread applicability of the continuous gas accumulation model has been questioned by some very good thinkers within the industry, and it needs to be approached with a great deal of caution. Whatever we finally conclude after continued study on our part and on the part of many others in the industry, whatever we conclude about the best model, the best approach, that's going to be applied in North America. It's going to be applied in other continents to identify the broad potential and the specific target areas. So this concludes my presentation. Again, I'd like to thank the SPE Foundation for its support of this lecture program.